Okay, this discussion is going to pick up where we left off in talking about intermolecular forces, and we're going to look specifically at some properties of liquids and how these properties are affected by the strength of intermolecular forces. Okay, the properties we're going to look at are surface tension, adhesive forces, cohesive forces, and viscosity. Okay, adhesion is the forces between the liquid molecules, the substance itself, and their container. Whereas cohesion, that's a measure of the forces between the molecules of the substance, or of the liquid in this case. So here we're looking at a slide. We have two different liquids on the same slide. And what we're seeing here is the difference in relative strengths of the adhesive and cohesive forces. So on the left side, we see that this liquid is all spread out, okay? And so in this case, the forces between the liquid and the surface of the slide are stronger than the forces between the liquid molecules. So our adhesive forces are stronger than the cohesive forces of the liquid. On the right side, here we have little droplets that have formed. And so here, the forces between the liquid molecules are strong and they're able to resist spreading out. So here our cohesive forces are stronger than the adhesive forces between the liquid and the slide. Okay, another example of something that's affected by the relative strength of adhesive and cohesive forces. This is the meniscus. And here we can see we have two different substances in a test tube. And this one on the left has more of a concave kind of meniscus, whereas this one on the right has got a convex meniscus. And so if you think about it, it's similar to the previous example we had. Here, where we have a convex meniscus, here the forces between the molecules themselves of this liquid are stronger than the forces between the liquid and the walls of the container. Whereas over here, the adhesive forces are stronger, and so we see a little bit where it's kind of pulling the liquid up where it contacts the test tube, and so we get that concave meniscus because the adhesive forces are stronger than the cohesive forces. Okay, surface tension. This is the resistance of a substance to an increase in its surface area. And so it's similar to the concept of cohesive forces, except here with surface tension, we're just talking about the forces between the molecules that are on the surface of the liquid. Okay, and so in order for it to spread out or to increase its surface area, we have to weaken these forces. So the stronger they are, the more it's going to resist spreading out. Capillary action. Here again we have an example of kind of an adhesive force at action. This is the spontaneous rising of a liquid in a narrow tube. If you've ever had your finger pricked at the doctor's office and they take the little tube and touch it to the drop of blood and the blood goes up in the tube, that's capillary action. Okay, so here what we see is we have a glass tube and a liquid going up in it. And so basically what happens is that the adhesive forces are able to pull the liquid up the tube, and they will do so until they are not strong enough to overcome the force due to gravity based on the mass of the liquid in the tube. So as the liquid rises up the tube, the mass of that column increases, which means the force of gravity increases. And so as long as the adhesive forces are stronger, it'll continue to rise up the tube. But once we have a strong enough force of gravity to where it balances out, then the liquid will stop rising. Okay, viscosity, another property of liquids, that is the resistance to flow. And just as you might kind of intuitively think that the stronger the forces are, the more it's going to resist movement. And that's true. And so looking here, if we look at these two liquids, the one on the right is flowing faster, right? If we assume that they started dispensing this liquid at the same time, the one on the right is flowing faster because it has a greater volume inside the container. And so it flows faster, which would imply that we have weaker intermolecular forces in the substance on the right than we do in the substance on the left. So weaker intermolecular forces would be less viscous, flows more easily. All right. Now, so basically the thing to start thinking about is that when we are comparing properties of a substance, all right, or the same property among different substances, essentially we are comparing strengths of intermolecular forces. So we're going to just kind of just summarize what we've talked about with regard to the strength of intermolecular forces, just to kind of help you as you're going through this. For similar sized molecules, okay, we can look at them based on, is it hydrogen bonding, dipole-dipole, or London dispersion? Okay, strongest to weakest. If we are comparing two substances where London dispersion forces are dominant, then we're going to look at the number of electrons present. More electrons is stronger London dispersion force. In dipole forces, all right, we're going to look at the polarity of the molecule. More polar molecules have stronger dipoles, means it's going to be stronger dipole force. Okay, for hydrogen bonding, you're looking at the more sites you have for hydrogen bonding to occur, which is typically a measure of the number of lone pairs on the electronegative atom. That means stronger or more prevalent hydrogen bonding. And an example of that would be, say we were comparing water and ammonia. Okay, if we look at these two, we've got hydrogen bonding capabilities in both. However, on the water, we have two places or two lone pairs on our electronegative atom with two hydrogen atoms that are capable of forming hydrogen bonds with adjacent molecules, whereas with the ammonia, we only have one lone pair on the nitrogen. And so just that one site is available for us to have hydrogen bonds. So fewer hydrogen bonds can occur with the ammonia as opposed to the water. And so as we would expect, the boiling point, for example, of water is much higher than the boiling point for ammonia. Okay.